The self-driving Thymio project is structured into two main tasks. If we provide a street set, can Thymio find the lane and follow it? But before we could begin solving these tasks, we had to solve some technical problems. Each time we started working with Mighty Thymio, we wanted to find a quick way to let Thymio always see the same portion of space. To accomplish this task, we used a sheet of millimeter paper. Here we drew a sample street of 9 centimeters width. The idea was to adjust the camera until obtaining this range of view from the robot camera. This is the portion of the space that is captured by the camera. So we selected a trapezoidal portion on this image that would have looked like a rectangle from a top-down perspective. The second issue was image processing. To improve performance, after decompressing the RGB image from the robot camera, we transformed the image into a binary NumPy array, so the perspective transformation that we saw was performed. Let's get started with the first task. We used a finite state machine to explore the environment until the robot finds the street. During this phase, all pixel values from the camera stream are summed for each frame. When this sum is above a proper threshold value, the robot can see the street. A similar technique is used to adjust the robot orientation in such a way that it can start following the lane. For the second task, we tried to find a control strategy to give the correct control action to the robot. When the robot is perfectly aligned with the street in an ideal trajectory, the camera will capture exactly what the robot should see. But when the robot is not on this ideal path, it captures something else. So the idea is to compute an error given by the difference between these two images, and to feed this error to a PID controller on the steering. In order to quantify the error, we split the image into 2 horizontal bands, and we computed the centroid of each band. And also, the global centroid was computed. The control action should take on account 2 main components. The first component is proportional to the slope of the line connecting the upper and lower centroids. It expresses the error of the angular position of the robot with respect to the street. The second component is a measure of the disalignment between the robot and the center of the street. Here, the error is the sum of these 2 components. The simulation shows the error behavior while the robot is following the lane. The left window visualizes the 2 error components in real time. The plot on the right shows the error value. When the sign of the error is positive, Mighty Thymio will turn right. Vice versa, when the sign of the error is negative, the robot will turn left. The control action is ruled by a PID controller. And now, enjoy good performing Mighty Thymio lane following. However, the error function presents limits. This animation shows the error trend when rotating the robot in place while facing a straight street pattern. For angles out of the range, plus or minus 45 degrees, the error sign is inverted, resulted in a wrong control action. For this reason, the error value must be kept inside the range of operability shown. These are examples of the limitations of the robot's control strategy. In this case, when the radius of curvature is too short, the robot cuts the curve. The fact that the robot does not follow the conjunction street set is because the algorithm is not designed to deal with horizontal lines. Finally, we tested it in situations of bad visibility of the lines. The robot interprets the random noise from the pictures as signals to go toward the wrong direction.